Yeah, welcome to my talk about WebAssembly and how you can speed up your web application with WebAssembly. Who of you ever heard of that? WebAssembly? Yes, that's so awesome! Really awesome. Last week I was on a conference and it was a .NET conference, and unfortunately in the .NET community it isn't that spread yet, so I'm really excited that you all know it. So maybe I don't, all good, I don't need it, but thank you. I do freestyle now. No, so it's really, really awesome to be here. It's my first time speaking at RuhrJS, so I'm really grateful, and it's a pleasure for me to be here and to have the opportunity to maybe tell you something new about WebAssembly. First, some words about me. Yeah, I'm Martina. Thank you for the nice, warm introduction. I'm a senior developer at Innovex. I'm also at Angular. Actually, I'm an Angular girl in generally. To sum it up, I'm running NG Girls. It's a free workshop one day on a lot of weekends. Like this weekend, we're in Rome, running a workshop with Angular, introducing the tech into for women. And I'm also running a couple of meetups like Angular Heidelberg, but now I moved to Leipzig, so I will go organizing Angular Leipzig. I'm also, since this month, ambassador at the Women Tech Makers group, who gets help from Google to even bring more IT and help more to have more diversity in the IT. If you have any kind of questions, feel free to reach out for me. I'm also a Google developer expert in Angular and web technologies, so you can find me actually in Google as well. And yeah, if you have any kind of questions or you want to know anything about Angular as well, just reach out to me, and we can talk. Because unfortunately, after this talk, I have to go already. But if you have any kind of question, just write me, and I'm pretty sure we can have a talk if you have any kind of questions. So what I'm going to talk today. First of all, I'm an Angular girl. Okay, that's good. But what is now WebAssembly? Where comes WebAssembly into the whole thing, and why C++? That is actually a long, long, long story, since I have two elder brothers. Yes, that's really horrible to have elder brothers, because they always tell you, oh, you shouldn't, you're doing this web browser stuff, and you're just making everything colorful and UI and clicky and everything. But we are the C++ developers. We are doing some really hardware stuff, and you're just running inside a web browser, you're so high level. And then I said, okay, guys, I will now write my master thesis in C++, and I will show you how to develop C++. So I got to know a little bit C++, or even a little bit more, and I liked it. So in my private time, I spent a lot of developing C++ applications, native desktop applications. And then I heard about WebAssembly, and then I was like, well, this means, actually, I could run all my C++ applications now in the web browser as well. And I was like, boom, this is so amazing. I can really compile now C++, and it runs in the web browser, or not even just C++, Rust as well, or Go, or even C# applications. And I was really overwhelmed. I thought I have to research on that, I have to dig deep into that. I really want to take a look into that. And that's how I came, even though I'm actually a front-end developer with Angular, that's my story, how I came then to C++ and WebAssembly. And that I want to show you today. I want to show you today what WebAssembly, the basics actually are, and the toolchain, like how you can actually compile it. I will show it to you in some kind of live demo. And I want to show you how you actually can call from JavaScript a C++ function. Like I will show you in a live example. And then a little bit further, what is the future of WebAssembly? Like, what are the next steps? Is WebAssembly actually already production ready? So let's start. First, a small disclaimer, I'm not talking about improving the runtime performance. I'm not talking about the network, the network performance, like how to optimize the request. I'm just talking about the execution performance of JavaScript in comparison to WebAssembly and in comparison to native desktop code like C++. So how is JavaScript executed in the web browser? I'm sure I'm not telling you something new. We have our JavaScript source code. It will get parsed to the AppSec syntax tree, and from that, it will return the machine code, and then the interpreter and compiler, like V8 or in V8 in Chromium and Chakra in Edge, like are compiling and executing it. There are quite a few steps, actually, and as we all know, we love the flexibility of JavaScript. We love to can declare a variable whenever we want. We love that we can initiate a variable with a string and later just put a boolean inside. That's really amazing. Or that we can dynamically create just as many properties as we want to an object. This is really awesome, but I can assure you this drives the V8 team really crazy, that they're trying to figure out how to increase the performance when developers doing stuff like that, because JavaScript, you can do this with JavaScript, but for a compiler, adding dynamically variables or reparsing variables is really, really costly for when it comes to performance. So I create a small example. You can find the source code for that on my private GitHub account. I'll share you later. So I just created an example, like I calculated prime numbers in JavaScript, C++, and then C++ compiled to WebAssembly. And here you can actually see that JavaScript, yes, I mean, like, I don't want to blame any of the core members that are actually developing all the JavaScript engines. They're doing a great job, but there is still, it's just not made for this language that it's so performant like compiled languages like C++. But as you can see, actually, C++ compiled to WebAssembly is just 20% slower if you would execute the same code as a native application, as a native desktop app. And this is actually really amazing. So what could you get out of that? Maybe you can think, okay, maybe high computation tasks, maybe I could extract them to C++ and compile them to WebAssembly. And I will show you how to do that, actually. So WebAssembly. WebAssembly is more than what's going on actually right now. So many persons are thinking about WebAssembly. Yes, I can finally play Doom 3 inside my web browser. This is so amazing. Who heard of that? Who heard of Doom 3? And who played that? It's, I mean, like in the web browser, it's really amazing, and it's in WebAssembly, this is so crazy. And there are even like Unity and the Unreal Engine, they're already ported to WebAssembly, and it's so amazing, you can play games inside the web browser. Okay, I love to play a lot of games when I was small, but when I was short, long back ago. This is really amazing, but of course you might think, okay, but I'm running a company. I cannot play games the whole time. I maybe want to use it in my business somehow. So what can I do with WebAssembly except of playing games inside a web browser? So let's start first what WebAssembly actually is. To wrap it up, WebAssembly is actually assembler code for the web browser, so-called low-level bytecode. We compile it. We compile C++, Rust, Go, C#. We compile with a compiler toolchain to something that is called WebAssembly or .wasm format, and then we just download it into the web browser and compile it over there. It's fast. As I already mentioned, the comparison is just 20% slower than the native code. It's, of course, portable and efficient. Portable because I can run it in every web browser, and as long as the web browser, we always know the one web browser. But I will keep this web browser out now. So in general, it's really portable, so WebAssembly can run in every single good web browser. Some web browsers still need improvement, but in every web browser. And the best thing about WebAssembly is actually you don't have to install anything. Maybe back then you know the days where you had to install Silverlight or Flash or something like that. Luckily, there's still some dinosaurs with Flash, and I don't want to say too much about that, but we had to install a lot of plugins. WebAssembly is standardized and has a specification through the W3C consortium. That means, having that said, that you don't have to install anything. It's implemented in your web browser, so you can use it immediately. And as well, it uses the existed sandbox system inside a web browser. That means actually untrusted, unsecure code can be run in the web browser without doing any harm on your local machine. I know there are always people who say the sandbox is of course not that secure as well, and I know that there are really good researchers team who are always breaking out of the sandbox, but, and to be fair to say that, but all the browsers of course really doing a great job to make it as secure as possible. So what it actually is, we compile our C++ in C or Rust or whatever code to WebAssembly, and the WebAssembly module is then in the web browser and can interact together with JavaScript, CSS, and HTML code. Having that said, means that WebAssembly is designed not to complement JavaScript, is to complement JavaScript, not to replace it. Good that to replace it, not to replace it. And this is really important because so many persons are thinking now, yes, I finally don't have to think about JavaScript anymore, but that's not true. JavaScript isn't bad. Nothing is bad when you're doing it correctly or you're doing it right, that you made not assigning properties later on and adding on again and again or reparsing. If you might just use TypeScript, for example, for having a type system, that you just have to use every tool in the correct way. So WebAssembly is just a complementation of JavaScript. You still need JavaScript and you will need JavaScript in the future as well, and this is good in my opinion. I'm a JavaScript fangirl. Nevertheless, so what are maybe the use cases for performance? Like, of course, video editing, 3D rendering, video games, music streaming, encryption, image recognition. So in sum, all high calculation tasks can be extracted to WebAssembly, and in the end, it doesn't matter if you then write it in Rust or C++ or Java. You can even compile Java to WebAssembly. It just means that, of course, it's already compiled. All these high computation tasks can run faster than JavaScript itself. So when you have 3D rendering, that's why, of course, all the first use cases for WebAssembly were actually all the physics engines, or were the games, to port the games to WebAssembly, because it has all the 3D rendering inside. And that's why it's really good to use WebAssembly exactly for this high computation. I cannot say this word right now, I'm so sorry. How is it pronounced? Computation, thank you so much. Computation. I will practice that now till next year. Computation. So, okay, we know WebAssembly now. We know how to, for what we can use WebAssembly and what is it for, what is it. Now we want to take a look into the toolchain, how we can actually compile it. Or if I want to use it, of course, after this talk, you will say, damn, this is so good, I want to use it. What do I have to do? What do I have to download? And like it always is in the web world, you open Google and you type in mscripten or you type in WebAssembly compiler, and then you get thousands and over thousands blog entries and content, and you don't know where to start. So I just want to give you a short introduction of the best practice common toolchain that is used here for C++ and WebAssembly. It's called mscripten. What mscripten does is it cross-compiles C++ to WebAssembly. Okay, it uses something that is called LLVM. For those who already implemented C++ application, I think they might know LLVM. It's more or less just an umbrella project for some compilers of C++ or debugger, or just tools optimizations for C++ compiling. As well, Emscripten support standard C++ libs. That means that libraries for network communication or for reading or writing files, like libc or the GLUT, that are just standard libraries in C++, they are already ported to WebAssembly. So if I include them, I don't have to compile them, or I don't have to write my own WebAssembly module for these libraries. There are already ports. And this is something you get shipped with when you download Emscripten. It also extends some LLVM optimizations. Like in JavaScript, we know this optimization like tree shaking. And of course, C++ has some optimizations as well. And Emscripten ships even more optimizations for having a perfect working together between C++ and JavaScript then. So this is how the toolchain actually looks like. We have our C++ files. We have our compiler of Emscripten. The CLang is just something like the compiler that is used from Emscripten of the LLVM. It makes use of the one of the compilers of this LLVM umbrella object. And then actually what you get is 3 files. When you compile this C++ or C code, you will get a JavaScript file, a HTML file, and a .wasm file. This .wasm file is our binary file. So why does it generate JavaScript and HTML file? This HTML file is actually optional. Emscripten offers you the possibility to create a small prototype. And for that, you can already run this HTML in your web browser. It's including the JavaScript file. And this JavaScript file actually fetches the WASM module. To not develop that on your own, just to test, for example, something, you can already generate these files to test out, to try it out. But actually the most important thing, of course, that you need is the .wasm file, because that is actually your WASM module that you have to then stream inside a web browser. Emscripten as well brings something that's called Emscripten SDK Manager. With the SDK Manager, you can just keep your whole toolchain updated. Just as a further information, you can, for example, tell the Emscripten compiler, don't use Clang or CLang, whatever, the pronunciation is always different, and use another one. Use GCC or other compilers than Clang. You can configure your toolchain with the Emscripten SDK Manager, and you can include like a package manager, like npm. You can import some other already ported libraries inside your web application. I would say enough of the theory. Let's get into how we can now finally call a C++ function from your JavaScript code. So I prepared something. It's a Fibonacci function. It's always a Fibonacci function. But let's say it like that. Let's think about this is the highest computation rendering task you've ever saw. Something that is, if you would run that in JavaScript, it would create like a deadlock and your browser would crash. It doesn't matter which browser. So what we like to do is we have our, this is our C code and this is our HTML file. In this HTML file, we will include actually the JavaScript file. The JavaScript file is the file that bridges, that has the bridge between WebAssembly and JavaScript, like the fetching, like the downloading of the WebAssembly module, and the compiling of the WebAssembly module. But we don't have to write this file, JavaScript file, on your own. We can just generate it. But first, we have to compile, of course, our C file to our WebAssembly module. So how we are doing this? First of all, we would compile this with our mscripten, but there's one thing, there's one optimization that would, if I would compile it now, not include this Fibonacci function. Could someone think about why? This Fibonacci function would not be in our compilation if I would compile it now. Could someone maybe think of something?
It's not being used.
It's not being used. It's tree-shaped. I mean, we are not calling it on our C code. There's no main in our C code where the compiler knows, we're using this. So we need to tell during the compilation time our compiler something like, trust me, I'm an engineer, I know what I'm doing, I use this later in my JavaScript file. So please leave it in our compilation, so please don't remove it. This is like a flag, it's called, really simple, mscripten keep alive. So please keep it alive, don't remove it. This is not a flag, or this is not a function that is shipped by any kind of standard library of C++. We have to include another library, another header, and this header is the mscripten header. So we include this as well here. So far, so good. So we are finished. Ta-da! And now we can just compile it. So how are we compiling it? We have our front end here. It's the EMCC compiler, the mscripten compiler. Now it says, okay, no input file. So I have to tell what I want to compile. Okay, I want to compile this Fibonacci C code. And now, and those who are already used C++ know the syntax, I have to tell an output format. Like with a -o, I can tell to what I want to have it compiled now. And what I can tell now is .html, .javascript, or .wasm. When I say .html, I will get 3 files, JavaScript, HTML, and wasm. When I say to JavaScript, I will just get JavaScript and wasm for a file. And when I just say wasm.wasm, -o.wasm, I will just get my WASM module, but then I have to take care of the bridging and downloading the JavaScript so-called glue code on my own. So since I have already the HTML file, I will create the JavaScript file, which will automatically generate me the JavaScript and the .wasm file. We can shortly take a look over here. This actually are just some fallbacks and some boilerplate code. We don't need everything here. But what we actually can see here is this WebAssembly instantiates streaming, and here we are fetching our WASM binary file. Like this is actually just the code we need. Like we just need 3 to 5 lines of code. We don't need the whole thing around. It's just a boilerplate code generated by mscripten. So what else do we need? I just saw that I forgot something to compile. So let's compile it again. I'm sorry for that. So because what I need as well inside the compilation is the bridge itself. Something that allows me to say, okay, a JavaScript module, call now the Fibonacci function. This bridge is called CWrap, and is a function that mscripten ships that allows me to call JavaScript, to call a C++ function from JavaScript. We have to tell the compiler, please compile it inside our compilation, and we do this by setting a flag. This flag is called, with -s you can set them, and it's called extra exported runtime methods. Yeah, you have your shell scripts or your make file. With mscripten you even have make files that are doing this for you, but it's always good to go through hell to know then the good parts of, to really know what's really good about all these makefiles and the other things. So as I said, what I will now bring inside the compilation as well is this runtime method, crep, which I then can call from the JavaScript code. Let's compile that. That's awesome, it's really fast. So let's use it here. So we call our module crep. Our module is now our WebAssembly module, crep, and let's copy paste it. Maybe it's better. We want to call Fibonacci. The return type is a number. So we kind of mapping now the function to JavaScript types as well. So the first type is the return type. The second, and the third parameter, would be the input types. That's why it's an array. We're just giving one integer inside. That's why it's just one number, of course. So one number. This returns a function. This returns a function, the function Fibonacci. So we assign it, and we call it awesome. Awesome calculation, most highest function. Now I will copy paste it. So far so good. We call it, and to make it a little bit easier, I just do a console.log. So now it should call our Fibonacci function, and it's good. How to test it? As I said, mscripten ships a lot, and it also ships an implemented web server. So, and we can run this app server by calling emrun. We call the browser we want to use. I'm sorry, I'm Google, so I have to use Chrome. And then, of course, the file I want to deliver. So emrun -1 browser Chrome app.html. Let's see. It's a blank page. It's not bad because we have a console.log. We have an error. Oh yeah, and it's called. You need to wait for the runtime to be ready. You can help me? Come on, it's actually a good error message. No. We're downloading something, we're fetching something, and fetching is always what? Asynchronous. So we need to create a callback. Damn. So, okay, there's a callback on the module, a callback function that is called onRuntime initialized. Phew, I'm pretty sure this can help us. It sounds at least like, I just noticed this long function names from other programming language, but it seems really obvious what this must do. So just put some brackets around it. And let's see if it's working now. And it's 89! Whoop, whoop! I mean, it's not 89, and it didn't just take some nanoseconds. It took like, I mean, if I would have implemented in pure JavaScript, it would have taken pretty sure 3 hours, because it's the most highest computation task ever. It's not just Fibonacci, there's some more behind it, trust me. Yeah, so that's actually how you can communicate between JavaScript and C++. So what is the future of WebAssembly? I can use it. Always, can I use always the best page for having this, for digging into, doesn't everybody knows can I use? If not, just go on it, can I use? Okay, you can type any kind of browser feature, any kind of ECMAScript version. You see as well where is it supported, and then you see all the browsers that are actually good. But there are also polyfills for Internet Explorer as well, so you can always run WebAssembly as well inside Internet Explorer. The roadmap. Yes, you can use WebAssembly, but till now just for languages with own memory management, like Rust or C++. Because WebAssembly itself doesn't have implementation of memory management yet. So yes, there is C#. C#, you can run C# already in the web browser as well. But what they are doing, they're compiling the whole mono runtime as well to WebAssembly and shipping it to the web browser. So that's how their memory management is working, and it works still great, but of course it's a little bit big. Multi-threading is a big thing, like especially for C++. It's not there yet. They had already like experimental stuff on that, but it's still working in progress. Direct DOM access. It's regarding like calling the DOM API directly from C++ or C. It's not there yet, but on the other hand, in my opinion, why would I need that? I don't use JavaScript for that. For 10 years, we are developing this great web browser APIs. I can even plug in my joystick and play Doom with my joystick inside a web browser. We have such great browser APIs till now. So, in my opinion, why should you use it? So, for me, it's not that bad that you can't access the DOM directly from C++. If you want to know more about that, about the roadmap, you can always go to the GitHub account of WebAssembly, and they're having a lot of documents and a lot of working examples as well, a lot of games as well that are already shipped inside a web browser, but like a really a lot of benchmarks as well, like where's the threshold of when is C++ WebAssembly faster than JavaScript, when you copying 3 items from one array to the other one, it might not be worth it to make a whole compilation of the WebAssembly module, then WebAssembly is faster. But when you use such, the bigger your objects are and the bigger your arrays are, and you're doing operations and the manipulation with it, then it might make sense to use WebAssembly for that. It's already used by a lot of things. Yeah, Twitch, I love Twitch. I always use Twitch for my procrastination. Actually, I don't know if you know that, but like you do that too, but I do that a lot. Unreal Engine, I said, Figma and Autodesk, they're all companies for having simulations inside a web browser, like to building architectures and stuff like that. And yeah. Summary, I'm sorry, I did a little bit 3 minutes overdue. Sorry. To sum up, WebAssembly ships C++ to the web browser. WASM binaries are faster to download and execute. They are actually cached in your IndexedDB, just as a side note. And the first 4 bytes are the version number. That's how they compare then what is the current version of the WebAssembly module. And WASM always performs better on large array size. There's a link, a hyperlink on that, which you can bring you to the HTML file. Yeah, to the resources that proves it. Thank you, that's good. So yeah, write me any questions if you have any. I hope you liked it. I hope you enjoyed it. And I hope you learned something new and might think about giving WebAssembly a try, because it's really there already and you can use it. So thank you so much. And here's my, I will Twitter the slides on Twitter. I will tweet the slides on Twitter, and there's my repo as well, where you can find a lot of examples, as well as the prime number calculation, and so on. So have a great coffee and a great 2 days.